By now you should have gone through this first part and learned a little bit about phase. Phase is it's a kind of a weird one. It describes, in theory, phase is just the position and behavior. But what we're going to start now is we're going to use phase when we compare waves. We'll talk about whether things are in phase or out of phase. For now, when we look at a wave on a string or picture it as a slinky, uh, what the phase is really what side of the slinky or what size of the string the wave is on. If it's on opposite sides, we call that opposite phase, and if we're comparing, if they're on the same side, we call that the same phase. Um, I'll get some diagrams out after, but sound also has phase, but since sound is one of these air pressure waves, we don't talk about sides. We talk about the phases to whether it's a high pressure or a low pressure. Uh, that'll make kind of a little more sense later. And as I said before, on its own, we don't hear phase. We hear frequency as pitch, we hear amplitude as volume. But if a sound wave hit me in the eardrum, I couldn't tell you the phase of that sound wave. If two hit me in the eardrum at the same time, then I could maybe do something with that. But that's getting ahead of ourselves. Okay, I'm going to talk you through a little bit of this interference stuff. First off, before we see what your intuition is, let me tell you that there are two kinds of interference. A kind that we call constructive interference and a kind that we call destructive interference. Of these two scenarios that I've stolen images from down here, scenario 1 and scenario 2, they both show a pulse. Whoever made this called the one A and the other B. And the first one, they are both kind of on what I would call the top of the slinky. Sometimes we call that a crest. So if two crests meet, what's going to happen? What do you think the interaction is going to be? And would you call that constructive or destructive? The second possibility, we've got a crest labeled A, a trough labeled B. What do you think is going to happen when they meet? And based on what you think is going to happen, would you call that constructive or destructive interference? I don't have a simulation for you to try on this one, so you're literally just using thought. Here's the answers. The first one was a constructive interference. If we have two waves that are in phase with each other, if they get to the exact same place at the exact same time, they combine in a constructive manner and make a larger wave. A key thing to notice is pulse A started on the left, and after the interaction where it was constructive interference, pulse A kept on going and ended up on the right. It's not like A bounced off. A just passed on through and kept on going in its original direction. Similarly, B was on the left. It'll be part of the overlap, and then after overlapping with A, B just keeps on cruising as if nothing ever happened. That's constructive interference, when two waves combine to make a larger wave. The amplitude was bigger. Destructive interference is the other scenario if we have what I call the crest overlap with a trough. They literally cancel each other out. If A and B were the exact same size, they cancel each other out. The amplitude decreases. If they're perfectly matched, then the amplitude would decrease to 0 for that split second. After the interaction, just like the constructive case, A would keep going to the right as if nothing happened. B would keep going to the left as if nothing happened. That's what destructive interference is. We say opposite phase waves are in the same place at the same time, and the overall outcome is we get a smaller wave. If they're perfect, then they'll completely cancel out. If they're a little bit different, then they'll make a smaller wave. But if they're exactly the same, then they would completely cancel out. The addition of these waves has a fancy physics name. It's called the principle of superposition. It's a fancy name, but all that it means is you literally just add them up. Same phase waves combine to make larger waves. Just literally add up the amplitudes. If they were exactly the same and each had an amplitude of 5 centimeters, then they would combine to make an amplitude of 10 centimeters for that split second when they overlapped. Out of phase waves combine to make smaller waves. In this little diagram, they are exactly the same. Let's say one was 5 centimeters tall, the other was 5 centimeters deep. The plus 5 and the negative 5 of the deep cancel out to make a 0. It's literally just addition. Principle of superposition shows up in other places in physics, so it's an important one that you'll hear about again and again. A little diagram here if you want to zoom in and take a look at that. Interference is a real thing and it's a big deal. If you've ever played on the water, you know that water waves can combine to make a really large wave. That's just interference. Or sometimes water waves combine and they cancel each other out. That's just interference. If they're making really large waves, that's a constructive situation. If they're canceling each other out, that's a destructive situation. Interference is all about changing or how the amplitudes combine. The same concept applies to sound. Sometimes sound waves can combine in a constructive manner and make a larger amplitude sound wave. Amplitude we've said is volume. So constructive interference means larger amplitude, that means it's louder. Similarly, if sound waves combine in a destructive manner, that means the amplitude has gotten smaller. Amplitude is volume, so smaller amplitude means it's quieter. Okay, let's flip to the engineering side. Let's say that you just learned this content and you wanted to engineer something cool that takes advantage of the interference of sound. More specifically, something that takes advantage of destructive interference. It's been done. Some of you are taking advantage of this technology right now, probably. Pause this clip and watch this clip, or here's another clip, a couple of them I found. As a spoiler, it's down here. Any noise canceling technology, there's two kinds. There's passive noise canceling and then there's active noise canceling. Any active noise canceling technology is really just applying destructive interference. If you're lucky enough to have Apple AirPod Pros or any other noise canceling earphones, earbuds, they've got microphones that are listening to the outside world, analyzing that sound wave of the outside world, and then creating a perfectly out of phase version of that sound wave that it plays towards your eardrum, so that the original outside world sound gets canceled by the out of phase version that the speakers create. So they're listening, analyzing the sound, and then creating a perfectly out of phase version to cancel it out. Another cool application of interference is this little bit. I created this PDF earlier, but in here there's a video clip of me actually doing it. But this is an easy one. There's no reason why anybody with a Chromebook can't do it. Open this link. It's a cool wave generator. You can tell it to play basically any sound you want. One that won't hurt your ear too much is 440 sine wave. So play that. Then open the same site in another tab, another window, whatever, and play a slightly different frequency. Play 442. So you should have the two of them playing at the same time. What does it sound like? Leave the 440 going and switch to 441. What does it sound like? Leave the 440 going and switch to 440.5. What does it sound like? Try it out. There's no reason why you can't try it. I've done it. You can watch the link. You're going to hear a loud quiet pattern, and the name of that is called beats. Here's a little graph to show you kind of what's happening there. Zoom in and look at it. But if you were to analyze it in certain points, so right about here, the one wave is in phase with the other wave. So they combine to make a constructive, a big amplitude, which you're going to hear as loud. A little bit later in time, the one wave is out of phase with the other wave. So they're going to kind of cancel each other out. Smaller amplitude, quieter for that split second. And if those two speakers are playing those same slightly different frequencies, we'll get an alternation of when they're in phase and loud and out of phase and quiet. That's the exact concept if you play instrumental music. That's the exact concept of how a music teacher tries to tune the different members of a band. They listen for those beats and they tell one person to adjust the length of their instrument to tune to try and hear those beats as spread out or as slow as possible. Okay, one last little bit for this video. Another place where interference shows up is in quantum physics. So when you come back and I teach you grade 12 physics, we're going to talk about quantum. There's a very, very cool experiment where they shoot what we thought were particles, where they shoot electrons through this cool apparatus called a double slit, which is literally just two narrow opens very, very close together. And when the electrons go through that double slit, like if electrons were true particles, when they go through a double slit, you should get a pile of electrons kind of behind the one opening, say over here, and a pile of electrons behind the other opening, say over there. So you should see like two bands. Maybe they'd be a little bit wide, maybe they'd be a little bit dispersed. But like if I threw snowballs through two openings in a wall, let's say, I'd get a pile of snow behind the one opening, a pile of snow behind the other opening. So the thought was electrons, since we thought they're particles, should behave the same way. We'd get a pile of electrons behind the one opening, a pile of electrons behind the other opening. But that's not what happened. When they did the experiment, it's a tricky experiment to do, but when they did the experiment, they found that an interference pattern was formed. Only waves can create interference patterns. So the fact that we can shoot electrons through this cool apparatus and get an interference pattern is experimental proof that electrons somehow have wave-like properties. So electrons behave like particles. We can see them hitting detectors, but they also behave like waves because they make an interference pattern. It's a very cool topic. We'll spend some time in grade 12 talking about it. If that tweaks your interest, you can, there's lots of cool stuff on YouTube, or let me know, I can direct you to some neat stuff. I'm going to pause this video here and then we'll start the next little one to follow up.